Air superiority determines the outcome of modern warfare before the first shot is ever fired. Only 6 nations on Earth possess the complete industrial capability to design, manufacture, and sustain advanced fighter aircraft from concept to combat deployment. These countries do not simply build machines. They project power across continents and define the strategic balance in contested airspace. Developing a 5th-generation fighter demands more than engineering talent. It requires sustained investment across metallurgy, aerodynamics, propulsion, avionics, and materials science. A single modern fighter program costs between $20 and $80 billion before the first operational squadron deploys. Supply chains span thousands of specialized manufacturers. Test programs consume years of flight data across extreme conditions. And behind every airframe stands a national defense industrial base capable of supporting combat operations for decades. Nations that cannot sustain this capability remain dependent on foreign suppliers. They cannot modify their aircraft to meet evolving threats. They cannot guarantee spare parts during conflict. And they surrender strategic autonomy to nations that control production. The United States operates the largest and most technologically advanced fighter fleet in history. American air doctrine prioritizes overwhelming technological superiority, network-centric warfare, and deep strike capability. The F-22 Raptor remains the world's premier air superiority fighter. With supercruise capability, advanced stealth geometry, and sensor fusion architecture, the Raptor dominates beyond visual range engagements. Only 187 were built due to cost and export restrictions, but no adversary has developed a confirmed counter. The F-35 Lightning II represents a different strategic calculation. 3 variants, conventional takeoff, short takeoff, vertical landing, and carrier-based, allow the United States and allied nations to deploy a common stealth platform across air forces, Marine Corps, and naval aviation. Over 1,000 F-35s are operational across 14 nations. This multinational production secures interoperability and collective deterrence. The F-15EX Strike Eagle extends a proven 4th-generation plus airframe with digital fly-by-wire controls, advanced radar, and hypersonic weapon integration. The Air Force ordered the F-15EX specifically to maintain magazine depth, mass firepower for peer conflict scenarios where stealth alone cannot guarantee victory. American industry now focuses on the next-generation air dominance program. NGAD aims to field a 6th-generation crewed fighter with loyal wingman autonomous drones, adaptive cycle engines, and open mission systems architecture. The objective is not incremental improvement, but maintaining decisiveness against rapidly modernizing adversaries. Russia inherits the Soviet Union's formidable aeronautical legacy. The Sukhoi Design Bureau produced some of the most capable fighter families in history. Russian doctrine emphasizes agility, heavy weapons payloads, and integration with sophisticated ground-based air defense networks. The Su-27 flanker family remains the backbone of Russian air power. The Su-35S variant features thrust vectoring engines, advanced AESA radar, and exceptional kinematic performance. It can carry 12 air-to-air missiles and engage targets at extended ranges. The platform has been exported to China, Indonesia, and numerous other nations, generating strategic influence and foreign currency. The Su-57 represents Russia's attempt to field a 5th-generation fighter. It incorporates low observable design, sensor fusion, and internal weapons carriage. However, production has been limited by funding constraints and engine development challenges. Fewer than 20 operational Su-57s exist. The aircraft reflects Russian design philosophy: super maneuverability, high speed, and weapons diversity. But Western sanctions complicate access to critical microelectronics. Russia's real strength lies in evolutionary refinement. The Su-30, Su-34, and Su-35 variants demonstrate continuous improvement of proven airframes. The Syrian conflict validated Russian aircraft in real combat conditions, reinforcing export appeal despite technology gaps with Western counterparts. China has achieved the fastest military aviation modernization in modern history. In 3 decades, the People's Liberation Army Air Force transformed from operating obsolete Soviet derivatives to fielding indigenous 5th-generation stealth fighters. The J-20 Mighty Dragon entered service in 2017. It features canard delta configuration, advanced avionics, and stealth shaping optimized for frontal aspect signature reduction. Over 200 J-20s are operational. The aircraft reflects Chinese doctrine emphasizing anti-access area denial and long-range strike in the Pacific theater. The J-16 multi-role fighter, derived from the flanker family, provides mass firepower. It carries precision-guided munitions, anti-radiation missiles, and air-to-air weapons. This platform mirrors the American F-15E Strike Eagle concept. Proven aerodynamics upgraded with modern sensors and weapons integration. China developed the FC-31 Gripen as a lighter stealth fighter intended for carrier operations and export markets. The design borrows from the F-35 configuration, but remains in prototype status. Whether the FC-31 achieves operational deployment will indicate China's capacity to sustain multiple concurrent advanced programs. Chinese progress depends on massive state investment, technology acquisition through various means, and an expanding domestic supply chain. Beijing now produces its own turbofan engines, phased array radars, and composite materials. The question is no longer whether China can build advanced fighters, but how quickly they can close remaining performance gaps with American platforms. Europe maintains fighter development capability through multinational collaboration and niche technological excellence. 3 nations, France, the United Kingdom, and Sweden, produce combat aircraft independently, while Germany and Italy contribute through joint programs. The Dassault Rafale represents French strategic autonomy. It operates from aircraft carriers and austere airfields. The Rafale has proven itself in Libya, Mali, Syria, and Afghanistan. France exports the Rafale to India, Egypt, Greece, and Qatar, demonstrating that European fighters remain competitive despite smaller production runs than American or Russian counterparts. The Eurofighter Typhoon resulted from British, German, Italian, and Spanish cooperation. It balances air superiority and ground attack roles. Over 700 Typhoons serve across Europe and the Middle East. The program demonstrates both the advantages of shared development costs and the complications of multinational decision-making. Sweden's Saab Gripen prioritizes cost-effectiveness and operational flexibility. The Gripen E variant features ASA radar and advanced electronic warfare systems in a lightweight airframe optimized for dispersed operations. Sweden exports the Gripen to nations seeking capable fighters without superpower political entanglements. Europe now pursues 6th-generation programs. France, Germany, and Spain collaborate on the Future Combat Air System. The United Kingdom leads the Tempest program with Italy, Sweden, and Japan. These initiatives aim to field networked combat systems integrating crewed fighters, autonomous platforms, and directed energy weapons by the late 2030s. European defense consolidation faces political and industrial obstacles. Work-share disputes, technology transfer restrictions, and divergent national requirements complicate every program. Yet Europe remains one of the few regions capable of indigenous fighter development, a capability most nations can only aspire to acquire. Several nations are attempting to join the exclusive circle of independent fighter producers. Their success will reshape regional power balances and the global defense market. South Korea's KF-21 Boramae program aims to develop a 4th-generation plus fighter with limited stealth features. Korea Aerospace Industries partnered with Lockheed Martin and Indonesian Aerospace. The KF-21 recently completed initial flight testing. If successful, South Korea will reduce dependence on American imports and potentially export to Southeast Asian nations. Japan operates a sophisticated air defense force, but historically relied on licensed production of American designs. The F-2 fighter, derived from the F-16, demonstrated Japanese manufacturing quality. Tokyo now pursues an indigenous sixth-generation fighter in partnership with the United Kingdom and Italy through the Global Combat Air Program. Japanese industry brings advanced materials, expertise, and electronics integration. India has struggled for decades to develop the Tejas light combat aircraft. Delayed by technological challenges and bureaucratic obstacles, the Tejas finally entered limited service. India now pursues the Advanced Medium Combat Aircraft, a stealth fighter intended for the 2030s. Success depends on overcoming persistent engine development failures and integrating complex foreign subsystems. Turkey initiated the TFX program after being excluded from F-35 procurement. The program faces obstacles, including engine availability, sanctions complications, and limited fifth-generation experience. Turkey possesses aerospace industry infrastructure, but transforming that base into stealth fighter production remains unproven. These programs illustrate the immense barriers to entry. Nations can design airframes and integrate subsystems, but developing competitive engines, stealth materials, sensor fusion software, and production-ready manufacturing at scale separates ambition from operational capability. Most nations will never produce advanced fighters domestically. The barriers are not merely financial. They are structural, technological, and institutional. Engine development remains the single greatest obstacle. High-performance turbofan engines require metallurgy capable of withstanding extreme temperatures, precision manufacturing tolerances measured in microns, and decades of iterative testing. Only 5 nations produce competitive fighter engines: the United States, Russia, China, France, and the United Kingdom. Even nations with advanced aerospace sectors often import engines. Stealth technology demands materials, science breakthroughs, computational design expertise, and manufacturing precision unattainable through reverse engineering alone. Radar-absorbent materials degrade and require continuous replacement. Maintaining low observable characteristics over thousands of flight hours requires industrial processes few nations possess. Sensor fusion, integrating radar, infrared search and track, electronic warfare, and data link systems into coherent battlespace awareness, requires software engineering at a scale comparable to operating system development. Millions of lines of code must function flawlessly in high-G combat maneuvers while processing terabytes of data. Finally, sustaining production demands continuous investment. Fighter programs span 40 years from initial design to final retirement. Governments must fund research, tooling, testing, production, and upgrades across political cycles and economic downturns. Most nations lack the fiscal commitment or strategic necessity to justify this expenditure. The next generation of air combat will not simply improve existing platforms. It will fundamentally alter the relationship between pilots and machines. Sixth-generation fighter programs prioritize 3 capabilities: enhanced survivability against advanced air defense systems, integration with autonomous loyal wingman drones, and open architecture allowing rapid technology insertion. The United States' next-generation air dominance program envisions a crewed fighter controlling multiple autonomous aircraft. These loyal wingmen will conduct high-risk missions, extend sensor coverage, and provide magazine depth without risking pilot lives. The system will adapt to contested electromagnetic environments using artificial intelligence and machine learning. Europe's Future Combat Air System and Tempest programs pursue similar architectures. All 3 initiatives emphasize network resilience, electronic attack resistance, and hypersonic weapon compatibility. Directed energy weapons may eventually supplement or replace missiles for point defense. Adaptive cycle engines will provide greater fuel efficiency and tactical flexibility. And digital engineering will reduce development timelines from decades to years. These programs will cost hundreds of billions of dollars. Only nations with existing fighter production experience can realistically attempt them. The gap between aviation superpowers and everyone else will widen further. 6 nations dominate modern fighter aircraft production: the United States, Russia, China, France, the United Kingdom, and Sweden. A second tier, Germany, Italy, Spain, South Korea, and Japan, contributes through collaborative programs. Everyone else depends on imports. This concentration of capability determines who shapes international security architecture. Nations that build fighters project power independently. Nations that cannot remain strategically constrained. Air superiority remains the prerequisite for modern military success. And air superiority belongs to those who control the technology, industry, and doctrine to design the future of combat aviation. Subscribe for more military aviation analysis. Turn on notifications so you never miss an upload. If you found this breakdown valuable, leave a like and comment one word: power, aviation tech.